Every year, over 1.5 billion tires reach the end of their service life worldwide, creating one of the planet's most challenging waste problems.
Nearly impossible to decompose naturally, a single tire can take up to 600 years to break down in the environment.
For decades, these discarded tires were seen as an unsolvable environmental burden, filling landfills and creating fire hazards.
Tire fires can burn for months, releasing toxic chemicals and creating environmental disasters that affect entire communities.
Standing water in discarded tires becomes breeding grounds for disease-carrying mosquitoes, creating public health risks.
Traditional disposal methods consume valuable landfill space and offer no recovery of the tire's materials or energy value.
But today, innovative recycling technology is transforming this massive waste stream into a valuable resource. Advanced recycling plants now process millions of tires annually, recovering materials for new applications.
The journey begins with systematic collection and sorting, separating tires by size, type, and condition.
Each tire contains valuable materials, high-grade rubber, steel reinforcement, and textile fibers, all recoverable through proper processing. This is the story of how waste becomes infrastructure, as millions of old tires are reborn as durable, rubberized asphalt.
The recycling process begins with systematic collection from automotive shops, dealerships, and collection centers. Specialized collection vehicles equipped with hydraulic cranes efficiently gather tires from multiple locations.
Each collection truck can transport several tons of tires in a single trip to the recycling facility.
Tires are transported from collection points across the region to centralized recycling facilities. Upon arrival, each load is weighed and documented for accurate tracking and environmental reporting. Digital weighbridge systems record the exact tonnage of incoming tire waste for processing records. Trucks discharge their loads in designated receiving areas, where initial sorting and inspection take place. Heavy equipment operators sort incoming tires by category: passenger car, light truck, and heavy commercial tires. Passenger car tires form the largest category, typically measuring 13 to 17 inches in diameter.
Commercial truck tires require separate processing due to their size and thicker rubber composition.
Giant off-road tires from mining and construction equipment present unique recycling challenges due to their immense size.
Forklifts transport sorted tire batches from the receiving yard to the processing facility entrance. Workers feed sorted tires onto conveyor systems that transport them into the shredding facility.
The tires now enter the processing facility, where systematic inspection and preparation for shredding begins. Before shredding, each tire undergoes inspection to identify and remove any incompatible materials.
Inspectors check for metal wheel weights, valve stems, and other attachments that must be removed before processing. Metal components are manually removed to prevent contamination of the rubber product and protect shredding equipment. Lead wheel weights, once common on tires, are carefully extracted for separate metal recycling.
Inspectors assess each tire's construction type, identifying steel-belted radials that require different processing parameters.
Foreign objects embedded in treads, from nails to stones, are identified and removed before shredding. Any tires still mounted on rims are processed through hydraulic separators that force the tire bead free. Metal detection systems provide a final automated check for any missed metallic contaminants. Tires triggering the metal detector are automatically diverted for additional manual inspection and cleaning.
Approved tires continue along conveyors to the primary shredding machinery, where size reduction begins.
Automated sizing systems route tires to appropriate shredders, optimized for different size categories. A final manual inspection provides the last opportunity to catch any issues before the irreversible shredding process.
Digital tracking systems record each tire's entry into processing, maintaining accountability and environmental compliance data.
With inspection complete, tires are now ready for the dramatic transformation from solid tire to shredded rubber. The primary shredder is the heart of the operation, a powerful machine capable of tearing apart hundreds of tires per hour. Massive rotating shafts equipped with hardened steel teeth create the shredding force needed to break down solid rubber. Hydraulic feed rams push whole tires into the shredder's rotating teeth at controlled intervals. Counter-rotating shafts grab the tire from opposite directions, generating tremendous tearing forces.
The rubber compound tears under stress, exposing internal steel belt reinforcement as the tire structure fails.
As the tire breaks apart, steel reinforcement belts are extracted and separated from the rubber matrix.
The shredder systematically separates tread sections from the sidewalls, breaking the tire into progressively smaller pieces.
Primary shredding reduces whole tires to rough chips, approximately 2 to 4 inches in size.
The primary shredder is driven by motors generating several hundred horsepower of continuous shredding force. 5-volume cooling systems prevent overheating during continuous operation, as friction generates significant thermal energy. Dust suppression systems capture airborne rubber particles, protecting workers and preventing environmental contamination. Operating continuously, the primary shredder processes tons of tires daily with remarkable efficiency.
Oversized pieces that missed adequate shredding are automatically identified and recycled back through the primary shredder.
Operators continuously monitor shredder performance, adjusting feed rates and power settings for optimal efficiency.
Multiple emergency stop systems allow instant shutdown if any safety issue is detected during operation.
Regular maintenance ensures continuous operation, with hardened steel teeth periodically inspected and replaced as they wear. The output from primary shredding represents the first major transformation, but further processing is needed to extract steel and refine rubber size.
Powerful electromagnets now separate steel reinforcement wires from rubber chips in a critical sorting step. As rubber chips pass beneath rotating magnetic drums, steel components are pulled upward against gravity. The magnetic field strength is precisely calibrated to capture all ferrous materials while allowing rubber to fall through.
Extracted steel is collected separately for sale to metal recyclers, recovering valuable material that would otherwise be waste. Eddy current separators use rapidly changing magnetic fields to eject non-ferrous metals like aluminum valve stems.
Non-magnetic metals are propelled forward into dedicated collection streams, preventing contamination of the rubber product. The resulting rubber stream is now free of metallic contamination and ready for further size reduction. Recovered steel is compressed into bales for efficient transportation to steel mills, where it will be recycled into new products. Each bale contains several hundred pounds of recyclable steel, representing significant material and environmental value. Steel bales are stored until sufficient quantity accumulates for economical shipment to recycling facilities.
Quality control technicians regularly sample the rubber stream, verifying complete removal of metallic contaminants.
Automated metal detection provides continuous verification that separation has been effective before rubber proceeds to grinding.
Air classification systems remove lightweight textile fibers from tire construction, further purifying the rubber stream.
With steel, aluminum, and textiles removed, the purified rubber is now ready for precision grinding into fine particles. Secondary granulators use rotating knives and screens to reduce rubber chips into precisely sized granules. Controlled feed systems meter rubber chips into the granulator at rates matching its processing capacity.
Rotating knife assemblies, spinning at high speed, slice rubber chips into progressively smaller particles.
The combination of rotational cutting and fixed screen openings creates uniform particle sizes.
Interchangeable screens with various mesh sizes allow production of different granule grades for specific applications.
For rubberized asphalt, granules between 10 and 30 mesh size provide optimal performance characteristics. Grinding generates friction heat, so rubber granules are cooled before further processing to prevent degradation.
Vibrating screens with multiple decks separate rubber granules into precise size fractions.
Oversized particles are automatically recycled back through the granulator until they achieve target dimensions.
Ultrafine rubber powder is collected separately for use in molded products and other applications requiring smaller particle sizes. Comprehensive dust collection systems maintain air quality by capturing airborne rubber particles throughout the grinding process. A final magnetic separation removes any steel particles that may have been introduced during the grinding process.
For ultrafine applications, cryogenic grinding freezes rubber with liquid nitrogen, making it brittle enough to pulverize.
The irregular, angular shape of granules provides mechanical interlocking when mixed with asphalt binder.
Processed rubber granules are stored in silos organized by size grade, ready for quality testing and blending.
Pneumatic conveying systems transport granules efficiently while preventing contamination and controlling dust.
Different granule sizes are produced to meet varying specifications for different asphalt mix designs. Computer systems continuously monitor production, ensuring consistent quality and optimal equipment performance.
Rigorous quality control ensures rubber granules meet strict specifications before being approved for asphalt production.
Samples are collected regularly throughout production for comprehensive testing and analysis. Sieve analysis verifies that particle size distribution falls within specified ranges for the intended application.
Each size fraction is weighed and recorded, creating a precise particle size distribution profile.
Specific gravity testing confirms rubber purity by detecting any remaining contaminants that would alter density. Magnetic testing verifies that steel content is below acceptable limits, typically less than 0.5% by weight.
Visual inspection under magnification identifies any remaining textile fibers that could affect asphalt performance.
Ash content testing measures inorganic materials in the rubber, ensuring composition meets specifications. Moisture content must be controlled below 1% to prevent foaming when mixed with hot asphalt binder.
Surface area analysis helps predict how rubber granules will interact with liquid asphalt binder during mixing.
Carbon black content analysis confirms the rubber's reinforcing properties that will benefit asphalt performance.
Only batches passing all quality criteria receive approval for shipment to asphalt production facilities.
Each approved batch is accompanied by a certificate of analysis documenting all quality parameters.
Certified rubber granules are now ready for transport to asphalt plants, where they'll be blended with bitumen. At the asphalt plant, rubber granules meet hot bitumen to create rubberized asphalt binder with enhanced properties.
Conventional asphalt cement is stored at elevated temperatures, ready to receive rubber modification.
Rubber granules arrive in bulk pneumatic tankers, ensuring contamination-free delivery to the blending equipment. Compressed air conveys rubber granules from the delivery truck into the plant's storage and metering systems.
On-site storage silos provide buffer inventory, ensuring continuous production capability. Hot bitumen is pumped from storage tanks at precisely controlled temperatures between 300 and 350 degrees Fahrenheit.
In specialized blending tanks, rubber granules are introduced to hot bitumen under controlled agitation. Rubber is added at rates typically between 15 and 20% by weight of the bitumen binder.
High shear mixing generates the mechanical energy needed to disperse rubber granules throughout the bitumen matrix.
Over 45 to 60 minutes, rubber granules absorb light oils from the bitumen and swell, forming an integrated network. Temperature is carefully controlled. as excessive heat can degrade rubber properties, while insufficient heat prevents proper blending.
Viscosity testing ensures the rubberized binder achieves the specified consistency for proper mixing with aggregate.
Completed rubberized binder is stored in agitated tanks that prevent separation and maintain blend uniformity. The rubberized binder now moves to the hot mix plant, where it will coat stone aggregate, creating the final paving material.
Stone aggregate is heated to match binder temperature, ensuring proper coating and workability of the asphalt mix. In the pug mill mixer, heated stone and rubberized binder combine, creating a homogeneous paving mixture.
The completed rubberized asphalt mix is loaded into insulated trucks for immediate transport to paving sites.
Time is critical, as the mix must remain above 250 degrees to ensure proper compaction and performance.
Modern asphalt pavers spread rubberized mix with precision, controlling thickness and surface smoothness. Trucks dump material directly into the paver's receiving hopper in a continuous operation. Auger systems distribute mix uniformly across the paving width, preventing segregation of materials. The heated screed plate both levels and initiates compaction of the rubber-modified pavement surface. The rubber granules are clearly visible in the fresh mix, distributed throughout the asphalt matrix. Breakdown rolling immediately follows the paver, applying initial compaction while the mix remains hottest. Pneumatic tire rollers provide kneading action that further densifies the rubber-modified pavement. Final steel drum rolling creates the smooth, dense surface that will carry traffic for decades. Quality control technicians verify that compaction meets density specifications of typically 92 to 96%.
The completed rubberized asphalt pavement represents the final transformation from waste to valuable infrastructure.
Rubberized asphalt pavements demonstrate superior performance, lasting up to 50% longer than conventional asphalt.
The rubber's elasticity provides exceptional resistance to cracking caused by temperature changes and traffic loads.
Rubberized asphalt reduces traffic noise by 3 to 5 decibels, significantly improving quality of life in urban areas.
The open texture created by rubber particles enhances drainage and wet weather traction, improving driver safety. Each mile of rubberized asphalt highway consumes approximately 2,000 scrap tires, diverting waste from landfills. Tire recycling reduces greenhouse gas emissions compared to incineration or landfilling, supporting climate goals. As environmental awareness grows, more regions worldwide are adopting rubberized asphalt for sustainable road construction. From waste problem to infrastructure solution, rubberized asphalt exemplifies the circular economy.